Aerial robotics is one of the fastest growing sectors of robotics. The commercial applications of drones have grown exponentially over the last decades, while researchers keep working on the grand challenge of making drones more agile, more efficient, and autonomous. But the story of drones actually started more than a century ago.
In 1907, there was two French guys actually coming up with the idea of quadrotors, which all of you probably know today. And then actually, exactly 100 years ago, there was actually the first one really flying up, but not very stable. What they didn't have at this time was electric motors. They didn't have actually electronic controllers. And of course, they didn't have IMU, which is extremely important to stabilize this system. So this actually somewhat died out. But the idea was a long time already around. Now, we started actually with quadrotor again, 100 years later, because we realized there is IMUs, small units which can actually measure accelerations and rotational speed. We have very fast direct drive motors, and we have the control unit which allow to fly this. And this was actually, to our knowledge, the first time such a quadrotor was up in the air and stably. It had even some ultrasound sensors which allowed to do collision avoidance. And they actually started a lot of movement. And you all know, meanwhile, millions of these quadrotors are sold all over the world for taking images from the air.
While quadrotors are now widely available, research on how to design and control drones is still very active. Current efforts are dedicated to the design of flying vehicles that are energy efficient and flexible. Quadrotors made of rigid materials are limited in their flying abilities because rigid structures restrict their ability to navigate complex, dynamic, or delicate environments. Instead, some researchers get inspiration from biology and try to mimic birds' flexible bodies and wings, allowing them to deform, squeeze through tight spaces, and interact safely with their environment. Soft and deformable rotors and propellers can be used in applications where traditional robots fall short.
Here, the critical aspects are related to combine the flexibility of the body of the arm and the variable stress of these arms with the propellers and being able to control. The design was very important, combining in the design the mechanical property, the resistance with the propellers and the aerodynamic properties. We have to combine both of them, and of course we have to control. It was difficult to control because, as I mentioned, the deformation with different stress in different parts, and then the vector of the propeller needs to be compensated, taking into account the model of the deformation of the arms. So everything is model-based. And finally, we were able to control modeling, but with very simple controller, but good modeling tools. And then we passed to the propulsion alternative. Two possibilities. One is to have flexible propellers. So you can see flexible propellers here. So you can put the stick, you can put the finger, and we can compute this, how this behaves after the collision, let's say collision. At the same time, more efficient in many cases, we put some embedded ducted fans in the arms to have in this way the ability to land, for example, adapting the body. And at the same time, we did the perching. Perching means many kinds of different perching with different prototypes that you have seen in the previous video. Again, we have to take obviously into account for the perching the aerodynamic effect, and particularly the ground effect. Obviously, the force that you have to exert depends on the ground effect and also the Coanda effect. So we model, and finally we are able to have this perching in different kind and different surfaces, adapting the body to different surfaces, which is not trivial.
Another way to imitate birds is, of course, to use flapping wings instead of propellers, which leads to higher energy efficiency. The research team at the University of Sevilla has worked on solutions for flapping wings robots, including design, modeling, actuation, control, perception, and perching.
We developed all these methods for the flapping wing, including the design, the modeling, actuation, control, perception and autonomy. Not only flapping, but we also added some components to have more payload and to have more energy efficiency, imitating the birds. Like, for example, this actuation in the tip of the wings, or also the passive joints and so on. And then we want to compute how is the energy efficiency. So we wanted to do that so you can see flying outdoor.
In addition to flying and carrying payloads, drones would benefit from the ability to do sharp turns and agile maneuvers like birds do.
Birds are not only capable of flying very efficiently for long distances without flapping a wing, but they can also perform very agile maneuvers. They can fly in confined spaces. They can avoid obstacles. And the way in which they do so is not so much because they flap the wings, but because they change the aerial surface and the direction of their aerial surfaces, which are the wings and the tail, compared to their velocity vector. And by doing so, they can change the total aerodynamic forces very effectively, and they can perform these agile maneuvers. So birds can transition between very efficient flight, very little energy consumption, to very agile maneuvers. We can build robots that approximate some of these morphing capabilities. And in particular here, I showed to you one that we built some time ago. It's a drone that is modeled partly on the northern goshawk. It's an animal that can fly very efficiently for tens or hundreds of kilometers with just a few wings flaps, and at the same time is a very agile predator. And what we studied here, we developed these artificial feather wings that can morph their surfaces asymmetrically or symmetrically, as well as their tail. So we built this drone in order to understand the contribution of synergistically moving the tail and the wing to perform agile maneuvers. And we learned a number of lessons by putting this drone in front of an open wind tunnel and on the top of a robotic arm. And we can use this information for actually programming the different sequences of tail and wing configurations that are required to perform these maneuvers. We developed an even more morphing and actuated drone, which actually models a raptor bird, that can also move, change the dihedral angle of the wings, and does not have any longer a vertical tail, a vertical structure on the tail. It can twist the tail just like birds can. And now we can, with this drone, we can ask a few more additional questions. And one of the interesting things is that biologists do not know how birds do, is the coordination of the wing twisting with the wing morphing to perform very agile maneuvers and rapidly turn the velocity vector, just like quadrupeds can do. But also biologists have noticed that birds, when they soar in the sky, they can turn without moving the wings at all. They're just moving the tail. But how can they possibly turn by moving the tail? The aerodynamic forces should be balanced. By using our drone and putting it in front of the wind tunnel, we realized that for raptor birds, like our drones has been designed, that have the tail very close to the wing, when the tail twists, the wake from the wings creates turbulent flow that cancels out the lift forces on one side of the tail, which generates a roll moment that makes the drone turn without moving the wings, or can help the drone contribute using to the turning using the tail. And of course, we could put this in practice. Here is in the lab. We can have this drone that makes different types of maneuvers to do gentle rolls without using the wings, or combining the wing and the tail to perform very agile maneuvers. Now, how can these drones become autonomous just like birds do? We should understand what are the type of optimization criteria that they use. And here, Graham Taylor, a professor at the University of Oxford, has studied different hypotheses about how actually birds do the perching maneuver, where they rapidly decelerate after a diving phase, and they climb up and they disperse or they dissipate almost entirely all the kinetic energy until they perch. And what Graham Taylor in this paper in Nature a couple of years ago hypothesized is that birds try to dissipate as much kinetic energy as possible when they arrive to the perching point, and they try to minimize the amount of distance covered at very high angle of attack, where essentially they are stalled, before reaching the perching areas. Whereas roboticists that have tried to perform this robotic maneuver with reinforcement learning or other criteria have always tried to minimize the amount of time covered by the drone from the transition state to the perching state. We actually validated Graham-Taylor's hypothesis. Here you have the bird, the drone, the physical drone, and the simulated drone. And we show that if the drone tries to perch using the optimization criteria that Graham-Taylor hypothesized, it will actually display the same trajectory, it will dissipate the same amount of kinetic energy, and it will show the same type of morphing capabilities that the birds, the same type of morphing sequence that the birds has. Instead, if you use different optimization criteria, you will dissipate much less energy, the drone will have a different trajectory. So clearly, now we also understand what the optimization criteria are.
In addition to agile flight, a challenge for flapping bird drones is how to efficiently perch and grasp objects.
It is very difficult to control and to cancel the perturbations. So we needed to compensate in the last meter by using this leg without degree of freedom to compensate by using visual servoing. We wanted to have not only that, but we wanted to have also manipulation. So we developed different beaks, manipulation sensing with the beak, but also manipulation while maintaining the equilibrium, which is difficult. We put some manipulator, very light manipulator on board the birds. And finally, we put two arms to manipulate, being able, for example, to take sample of stems and leaves. And finally, the cooperative manipulation between two.
Flying stably while interacting with the environment, for example, applying forces to objects, is a challenge for drones. But some birds can do it effortlessly. How can the same ability be transferred to robots?
What if we could actually fly in physical interaction? And we have in the nature wonderful examples that you can hover and in parallel actually exert forces to the environment. Now, typically, airplanes, flying robots are under-actuated. So you cannot freely choose the attitude and the direction or the movement in all directions. This is perfectly okay for flying, for taking images in the air. But if you want to exert force to the environment, if you want to approach really and get in touch with the environment, you need at least fully actuated systems, meaning in air you need 6 degrees of freedom to control, or even overactuated. And typically you end up in an overactuated system, as you can see it here, 6 propellers, but they are rotated around their central axis. So with this, you can actually generate a lot of different thrust vectors, or all the thrust vectors you imagine, which means that you can fly up and do pure rotation without flying away, or flying up, staying horizontal, and moving in XY. So you have potential to do a lot of different things, but at one point it's getting very difficult to control. Today we have these wonderful tools we know also from walking robots, for example, which allows us in simulation to train different policies. And what we started to do is also to train a policy of this system to open a drawer. So you do this in the simulation with enough steps and a good model. And I think it's important always you need a good model so that you can really transfer then the control. You transfer it to the real system and you can see all of a sudden the system is capable to really do physical manipulation.
But what about perception? How do birds perceive their environment and use this to control their motion? And how can drones do the same to become fully autonomous?
We are inspired by the fact that there are many stunning examples of visual perception in nature. So have a look at this one. Look at these birds, how they fly together without crashing into each other, and they coordinate with each other to create these beautiful formations. Now, if we really want robots to be around us and interact in the same space as us, we also want them to understand their workspace and be able to interact with it in a similar way. So there's many things that we still need to work on. In particular, we would like to be able to track faster motion, have the ability to deal with larger scales, richer maps. We want our algorithms to be more robust and we want them to perform at less computation. So basically, we want a bit of everything. So if I am to summarize all of this in one point, we would really like to handle larger amounts of data more effectively. And in robotics, in contrast to computer vision, we constantly have to balance out these two competing goals, precision versus efficiency. And every algorithm has its own different balance. We would like to have a team of robots, let's say small aircraft, that that they're equipped with some kind of vision sensors, let's say cameras for now. We would like to develop their visual perception and intelligence that will enable them, first of all, as individuals, to navigate in space autonomously, and then collaborate in a team to do a useful task together. For example, to build together a common map of their workspace or a reconstruction of their workspace. So challenge number one is, how do we robustly localize and map the environment?
When a robot starts flying, it knows nothing about its environment. It needs to build a map, and at the same time to localize itself in it. But how can localization and mapping remain robust against changes in luminosity or weather conditions? One way of dealing with it is to fuse information from visual, LiDAR, inertial, and GPS sensors. Current methods for simultaneous localization and mapping use a discrete set of motion estimates from multiple sensors to approximate how the sensor suite has been moving. The syncing of the sensors is very important, and that calls for expensive sensor hardware. Attempts are being made at using continuous time slam, still approximating the real trajectory, but with continuous functions and asynchronous sensor information.
The second challenge is to build a denser scene representation, a richer scene representation. Why? Because if we want our robots to be able to interact with their environment, for example, to reach out and grasp an object, or to avoid obstacles while flying, then we need them to build this, at least local, dense representation of the scene.
A dense representation of the environment, for example, can be used for autonomous emergency landing. RGB images, SLAM data, and semantic information can be used to train a deep reinforcement learning strategy that selects the safest landing spot, selects the best motion to get there, and feeds it to the drone controller.
And after many failures and attempts and successes, we had successes. You can see one example on the left of a successful landing, and two examples of failure cases on the right, where on one side the vision is failing us, where there are no features on the lamppost, and in this case it's summer or winter in Zurich, I don't know, and the terrain is, the bushes are classified as terrain, they have the same color. And finally we have the third challenge. Imagine you have these very clever individuals, agents moving in space. How do we get them collaborate with each other to do something useful? For example, to build a common map of their workspace. So we have two drones that they take off, they know nothing of each other, but as soon as they take off, they each start individually mapping their world, and they dump all that information down to a ground station, a laptop, and that laptop starts processing all of that information and keeps it as a kind of bookkeeping. And then if it recognizes that these two drones are actually at the same place, it informs them, hey, you guys are actually at the same place. Or if another agent is going to a place where some other agents have been to before, it sends it a portion of the map.
These new capabilities can be transferred from drones to other platforms. Here, for example, visual sensors, LiDARs, and inertial sensors are mounted on an excavator that can autonomously scan the area for stones. Select which ones to pick up and use them to build a stable wall.
With these three challenges, we aim to teach robots to see and collaborate, because we believe that this is what we really need to revolutionize the way that we perceive robotics today.